Hi scholars, Ms. Beglin here with your Unit 1, Lesson 3 Independent Edpuzzle work on making ions. Before you continue with this video, please complete the drill in the Edpuzzle. Now that you've completed the drill, let's keep going. This unit has been about atomic structure and periodicity, and so far we've explained trends that we see in the groups and periods of the periodic table. We've extensively discussed ionization energy and successive ionization energy. But how do we actually make ions? How do we measure ionization energy? The answer is relatively simple. The most common way of ejecting an electron from an atom, or ionizing that atom, is by hitting atoms with electromagnetic radiation, or light, with enough energy to overcome the attractive force between the electron and the nucleus. Some of this should be familiar from physics, but light behaves like a particle and a wave. We call particles of light a photon, and generally speaking, we describe light using the characteristics of wavelength and frequency. Wavelength is the measure of the wave from crest to crest. Its variable is this little upside down y, which is the Greek letter lambda. It is measured in meters or nanometers. You should be able to convert between these two using the knowledge that 1 meter is equal to 1 times 10 to the 9th nanometers. So nanometers are really small. Frequency is the number of waves that pass a point per second. Its variable is this little V-looking thing, which is actually the Greek letter nu. So let me write that out. Nu. Frequency is measured in per second, or 1/second. You may also see this as hertz, or Hz. That just means 1/second. Here you can see a diagram of the electromagnetic spectrum. As you can see, wavelength and frequency are inversely proportional. So as wavelength increases, such as over here, frequency decreases. And as you can see over here, as wavelength decreases, frequency increases. The shorter a wave is, the more waves can pass a point in 1 second. And this kind of makes sense. If I make a wave that's very large with my finger, I'm moving kind of slow. But if I make really, really small waves, it can move really fast. Here we see a depiction of the electromagnetic spectrum, which really highlights how small the visible light spectrum is. The range on the visible light spectrum is from 400 to 700 nanometers. And that is a range that you should be familiar with. Now, we've already seen that wavelength and frequency are inversely proportional. We can actually relate the two mathematically using this equation that is found on your AP Chemistry exam reference sheet under the section Atomic Structure. This equation is read C is equal to lambda nu, where C is our speed of light, 2.998 times 10 to the 8th meters per second. We can also relate our frequency and energy using the equation energy is equal to h nu. where H is Planck's constant, 6.626 times 10 to the negative 34th joule seconds. Sometimes you'll be given the wavelength and have to solve for frequency before you can use this equation. Rearranging this, you would get that nu is equal to C over lambda. So the next time someone asks you what's nu, you can say C over lambda. Haha, get it? Let's work through an example problem. A laser emits light that has a frequency of 4.69 times 10 to the 14th hertz, or per second. What is the energy of one photon of this radiation? I'm going to highlight the equation or annotate the question for my key information. I'm working with light. It has a frequency of 4.69 times 10 to the 14th per second, and I'm asked to find the energy. I'll refer to my equation sheet and recognize that the equation E is equal to h nu, relates frequency and energy. Plug in my variables. H is Planck's constant. Nu is the frequency. And I get that the energy is 3.1 times 10 to the negative 19th joules. Now, scholars, 3.1 times 10 to the negative 19th joules is not the exact answer that I got. I cut off the numbers after 3 places. The reason I did that is because there are only 3 places in the numbers in my calculation. This process of selectively choosing where to end your response is referred to as significant figures. And we'll learn more about it as we go. Let's move to part B. If a laser emits a pulse containing 5.0 times 10 to the 17th photons of this radiation, what is the total energy of that pulse? So I've already highlighted how many photons I have and what I'm being asked for, the total energy. I know from part A that one photon has 3.1 times 10 to the negative 19th joules. So if I have 5 times 10 to the 17th photons, I should have 0.16 joules. And I can just multiply them as you see. Again, I stop at 2 significant figures because my calculation is limited by the one that I have the least of, and I have 2 significant figures at one point in the calculation. All right. Oh no. Well, let's move to part C. If a laser emits 1.3 times 10 to the negative 2 joules of energy during a pulse, how many photons are emitted? Again, I know from part A that one photon has 3.1 times 10 to the negative 19th joules of energy. So I can convert from joules to photons and find that there are 4.2 times 10 to the 16th photons in this burst of energy. This makes sense because it's less than 5.0 times 10 to the 17th photons, because 1.3 times 10 to the negative 2 is less than 0.16. So energy is directly proportional to frequency, which is inversely proportional to wavelength. So as wavelength increases, frequency decreases. That was an ugly one. And energy decreases. Or as wavelength decreases, frequency increases, and energy increases. That's all, folks.